If we need to find the antiderivative of the sum or difference of f and g, so the sum and difference of two functions, all we need to do is take the antiderivative of the pieces. So the antiderivative of f of x and the antiderivative of g of x, and then either add or subtract, whichever is appropriate. So let's take the antiderivative of the quantity 4x to the fifth plus 5x dx. This is a sum, so I'm going to break this up into the antiderivative of each of the pieces. So I'm going to need to take the antiderivative of 4x to the fifth dx and add that to the antiderivative of 5x dx. Using our constant rule that we just talked about, I'm going to pull the 4 and the 5 in front of the antiderivatives. So I get 4 times the antiderivative of x to the fifth dx plus 5 times the antiderivative of x. Applying our power rule, we get 4 times x to the sixth over 6 plus 5 times x squared over 2 plus our constant. And now we could simplify this if we really wanted to. Here's another example, but now this one involves the variable t. So all our rules will apply to t because we're doing this with respect to t. So the antiderivative of square root of t plus 3t minus pi dt. So we have both sums and differences here, but our rules say that we can break this up into the individual antiderivatives. So I'm going to take the antiderivative of square root of t dt plus the antiderivative of 3t dt minus the antiderivative of pi dt. I'm going to need to do a little bit of work to simplify this so I can use my power rules that we've talked about before. So the first thing I'm going to notice is square root of t is the same as t to the 1/2. If I write this as t to the 1/2, now I can use my power rule to figure out what the antiderivative is. On my antiderivative of 3t, I'm going to pull the 3 out in front. And on my antiderivative of pi, I'm going to pull out a pi in front, leaving me with a 1 in the antiderivative. So let's go ahead and apply our power rule. When I raise the power and divide by it on t to the 1/2, I get t to the 3/2 divided by 3/2. When I take the antiderivative of t with respect to t, I get t squared over 2, and then I'll multiply by my constant 3. And the antiderivative of 1, well, the derivative of what gives me 1? Well, the derivative of t is 1. So I get minus pi t, and then of course I have my integration constant on the end. If I were to go ahead and simplify this, dividing by 3/2 is the same as multiplying by 2/3. So the first term would be 2/3 t to the 3/2. I might put the 3 and the 2 in this fraction together as 3/2 and then multiply by my t squared. And then I have minus pi times t plus c. Now, as our antiderivatives get a little more complicated, our goal is to always, as much as possible, try to write this so we can apply our power rule. So in this case, I'm taking the antiderivative of the quantity 3x to the 6 minus 7x to the 4th, all of that divided by x squared, and I'm taking the antiderivative with respect to x. So the first thing I'm going to do is I'm going to divide that x squared into both terms on top. So I'm going to take the antiderivative of 3x to the 6th divided by x squared, and I'm going to subtract the antiderivative of 7x to the 4th over x squared, and I'm going to do this with respect to x. I have this difference, so I'm going to break this up, but before I do that, I'm going to go ahead and reduce x to the 6th over x squared to x to the 4th, and x to the 4th over x squared as x squared. Now when I break it up and I pull out my constants, I'm left with 3 times the antiderivative of x to the 4th dx minus 7 times the antiderivative of x squared dx. Now we're in a perfect position to go ahead and apply our power rule. So in the first antiderivative, we get 3 times x to the 5th over 5 minus 7 times x cubed over 3. And since I've taken my antiderivative, I add on the plus c integration constant at the end. Simplifying this a little bit, I get 3/5 x to the 5th minus 7/3 x cubed plus c. Remember, we can always check to make sure we've done these correctly by going ahead and taking the derivative of the answer and seeing if it gives us our original integrand up here.